Okay, this is 12.4 solenoids. Now that's a funny word that we're going to learn what it means very soon. On the last lesson we were looking at electromagnetism. We were looking at the idea that running current through a wire produces a magnetic field. This was a huge discovery, it really changed a lot of things, and it got a lot of physicists very, very excited. Now, there's a couple other pieces of information that go along well with that. The first piece of information here is that is about how magnetic fields interact. So here, if two field lines point in the same direction, they repel. So if two field lines point in the same direction, they repel. And likewise, two field lines in opposite directions attract. So this is a really useful principle that is used in all sorts of technology nowadays. And why it's important, connected with what we just learned in the last lesson, is this example here that two wires with opposing currents repel. So there's a picture here. If I have two wires right beside each other, and one of them the current is coming out of the page here, one of them the current is going into the page, you can see they produce magnetic fields. This one is going in this direction here, and the other one is going in the other direction. So this one's going in clockwise, the other one was going in counterclockwise. You can see that in the middle here, those field lines are going in the same direction, which means that they repel. It makes, you can see there's a force here and a force here. The wires are forced apart, away from each other. And that makes a lot of modern electronics possible. Okay, so connected with that is this idea of solenoids. Now solenoids are coiled conductors. If I take a single wire can be wrapped in a coil. Which produces very interesting and useful magnetic fields. So the way the magnetic fields of this wire interact with each other, it's a single wire, but it's wrapped around in a circle so that its magnetic field ends up interacting with itself. It creates a very interesting result that ends up looking exactly like, or very similar to, a bar magnet. And so by running electricity through a coil of wire, we can produce an artificial magnet. And we call those electromagnets. So these coils that I was just describing are electromagnets. Now, electromagnets are magnets that turn on by running current through them. So normally it's just a coil of wire, not really doing anything. When you send electricity through that, when you send current through it, all of a sudden it becomes a magnet. So that's an electromagnet, and that has a lot of uses. So what's this word solenoid? Well, solenoid is just the proper term or the proper name for a coiled conductor. So when you have a coiled conductor like that, a bit of wire that's coiled around in a circle, you know, and what I'm talking about here is if I take my wire and I sort of make it look like a slinky like this, we call that a solenoid. All right, so we've got a couple pictures down here. The first one is of just a single loop of wire. And you can see that we have our positive, which means that our conventional current is flowing from this end. I'm going to use a different color here. From this positive end to the negative end. So our current is going in that direction. And you can see that there's a whole bunch of iron filings there, and those iron filings show us the fields that are being produced. So you can see we actually get sort of a straight vertical field down the middle, and then we get these sort of circular fields going like this. And that's drawn on the next picture here. So this first picture is for a single coil. This is a diagram of that same thing. You can see we have the current coming out here, current going in. Good. This next picture here is a picture of a solenoid, where we take that idea from a single loop and we extend it by having loops after loops after loops. And you can see that the way those fields add up, we end up getting a field that runs straight down the middle, like this, and we get fields coming off like this, going off in circles, like this, and that ends up looking exactly like what our bar magnets look like. So this is a bar magnet here. So that we can produce an artificial bar magnet. Here we had north to south. I might have drawn, on the previous picture, I might have drawn the directions wrong, I'm not sure. But that's the idea. Okay, great. So we have this new technology now. We can take a coil of wire, run electricity through it, and we get a magnet out of it. We have a new right-hand rule for this. I promised you we were going to have 3 right-hand rules total. So this is right-hand rule number 2. My comment here is just to remind you, we learn about 3 right-hand rules total. So this one is number 2. It works the same way with our thumb and our coiled fingers. So the right-hand rule for a solenoid is if you coil the fingers of your right hand around a solenoid in the direction of the conventional current, your thumb points in the direction of the magnetic field lines in the center of the coil. Okay, so we've got our coil over here. Our current is going up this way. You can see that it's coiling around like this, going around in a circle like this. So I want to coil my fingers, I want to curl my fingers in that direction. You can see that that's what we're doing. We're curling our fingers in that direction. If we do that, my thumb points in that direction, which means that's the direction of my magnetic field in the center of the solenoid. So that ends up becoming the artificial north pole, and this becomes the artificial south pole, because we've got our magnetic field going in like this. And then I could continue to draw this, having this sort of a shape, like a bar magnet would. So that becomes our north pole and our south pole. All right. So we've got a couple examples down here to sort out, and then you've got your homework problems. So let's see. We have our fields coming up like this, like this, like this. So if you look above, that's like our single coil here. And the question is, what direction should those fields be going? Well, the way you can think about this one is look at either of these wires independently. If I just look at the one on the left here, if I just look at this one, and if I have field lines going like this from it, well, I curl my fingers in that direction. That means that the current needs to be coming out from this guy because my thumb points towards me. And likewise on the other one, my field lines are going like this. Well, I curl my fingers that direction. My thumb is pointing into the page, so that needs to be an X there. Okay, so that one isn't quite using the solenoid rule. That's using the rule from the last page. Likewise here, I've got a dot coming out. It actually looks just like the picture on the left here. So the dot coming out, the field lines here are going to look something like this. Okay, and at the center, they become pretty much a straight vertical line. Going in, this guy looks like this. So there's our field lines in that situation. Okay, now we have a coil. Now we have a solenoid. So our current goes from positive to negative. So our current is going in this direction. So it's coiling around like that. So I want to coil my fingers in that direction, and that means that I get a magnetic field going in this direction. And this becomes my north pole and my south pole. Okay, and finally here we have a picture with a battery, and this requires you to know what the positive and negative ends of a battery are. So the large end is the positive, small end is the negative. So we have current coming out this way, going this way, behind the loop, and coming back out. So if I coil my fingers in that direction, my thumb is pointing this way. This becomes my north pole, this becomes my south pole. And there we go. That's how these problems work. Have fun with the homework.